Hi, welcome back to my channel, and for today's video, we will be talking about the exponential function of complex numbers. Thank you so much for your undying support, and if you are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. So if you have any questions or clarification, don't hesitate to comment down there so that I would know and we can discuss on that. Okay, so let us recall that from the exponential function of real numbers, let's say we have f of x, and that's equal to e to the x. So this is an exponential function of real numbers. Then we have the property saying that number 1, e to the x is continuous on the set of real numbers. And your e to the x is greater than 0, implying that your e to the negative x is equal to 1 over e to the x, and it's still greater than 0. Number 2, your e to the x approaches infinity if your x approaches infinity, which means to say that your e to the negative x approaches 0 as x approaches infinity. Okay, number 3, e to the x is equal to its derivative. Number 4, your e to the x has the power series equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on for every x in R. And number 5, this property holds that if you have x1 and x2 elements of real numbers, then e to the x1 times e to the x2, that's simply the same as e to the x1 plus x2. So your x1 and x2 here are reals. I would also have to add things that the function f of x equals e to the x maps the set of real numbers 1 to 1 onto the positive real numbers. So, if this is 1 to 1 onto, mapping from the set of R to the set of positive R, then it has a continuous, strictly increasing inverse function called natural logarithm, which means to say that you have ln, so that's the natural logarithm, ln mapping from r plus to r, defined by this. You have x equals ln of y if and only if y equals e to the x. That's it. So we have now the question here. Can we extend the definition of the real exponential function to the complex case? If so, what properties remain the same? Which means that if you have e to the z here, and your z is an element of the set of complex number, then we can write z here equals x plus iy. Your x and y, of course, are reals, and your z is a complex number. Then I can write this in this way, e to the x plus iy, which is equal to e to the x, e to the iy. Now, following the same method with expressing e to the x, the real exponential function converted into a power series, if I'm gonna follow that way, the same with e to the iy, then I would have 1 plus iy plus iy squared over 2 factorial plus iy cubed over 3 factorial plus and so on, which if I will rewrite them in this way, I would have 1 minus y squared over 2 factorial plus y to the 4 over 4 factorial plus and so on, and I would have this imaginary part as y minus y cubed over 3 factorial plus y5 over 5 factorial and so on. So if you have any questions or clarifications on this, you can comment down there. But you can just double check that this second expression here is the same as with the first expression above. And observe that this is the power series representation of cosine y, and this is the power series representation of sine y. So that means I can write this as cosine y plus I, and this becomes sine y. So your y here is an element of the set of real numbers. So which means that e to the iy is the same as expressing cosine y plus I sine y. Now observe that using the same familiar de Moivre law, your cosine y plus I sine y raised to n, that's the same as cosine ny plus I sine ny, which further implies that e to the iy raised to n is the same as writing e to the ny. And so, the modulo of e to the iy is the same as the square root of cosine squared y plus sine squared y, and that's equal to 1 for every y in R. So if we assume our y to be equal to pi, then we have e to the pi I plus 1 is 0. And in fact, this is the most beautiful equation as claimed in the complex analysis. So properties that are being reserved also in the complex case is when if you raise e to the I y sub 1 times e to the I y sub 2, that is the same as e to the I times 1 plus y sub 2. And we can also justify easily that e to the z1 times e to the z2, that's the same as e to the z1 plus z2, and your e to the z1 over e to the z2, that's the same as e to the z1 minus z2, and e to the z raised to n, that's the same as e to the n z for every n which is an integer. Hence, by the above result that we've discussed earlier, the modulo of e to the z, that's the same as the modulo of e to the x, e to the iy. And if you remember, we've shown that the modulo of e to the iy is 1 because I can write this in this way. E to the x, I don't need to use modulo anymore because we've known already from the very start of this video that e to the x is always greater than 0. So we have to multiply that by e to the iy. And remember, this is 1, so therefore the modulo of e to the z is the same as e to the x. And this will hold, of course, when z is e to the z is not 0 for every complex number z. However, we always have to remember that the complex function e to the z is not 1-to-1. Okay, in fact, if I'm gonna write this e to the z plus 2 pi I can write this as e to the z e to the 2 pi I, and that's equal to e to the z times cosine of 2 pi plus I sine of 2 pi. And if I'm gonna evaluate this, that's equal to 1, so therefore that's equal to e to the z. Now next, suppose that our e to the z equals e to the x plus iy, then this is equal to 1. This means to say that e to the x cosine y, that's equal to 1, and e to the x sine y is equal to 0. Now since e to the x is not 0, then we are forced to conclude that sine of y is 0. That is, our y is equal to n pi. Your n can be any integer. However, if we substitute y equals n pi into this thing here, so if we substitute this in this thing here, we have e to the x cosine n pi, and that is equal to 1. So n must be even integer. And in this case, our x is 0. Hence, z is an integral multiple of 2 pi I. That is, our e to the z equals 1 if and only if our z is equal to 2k pi I for some integer k. Okay, so collectively summarizing what we've discussed earlier, we will have to introduce the theorem saying that the equality of e to the z1 equals e to the z2 holds if and only if your z1 is equal to z2 plus 2k pi I for some integer k. Since we've shown that z is an integral multiple of 2 pi I. That's it. E to the z here is equal to a plus ib. Your a, of course, is not equal to b, not equal to 0. So this would imply us that e to the x cosine y is equal to a, and your e to the x sine y equals b, which further implies that e to the 2x, this becomes cosine squared y plus sine squared y, which is equal to e to the 2x, because this thing here is equal to 1. And that's equal to a squared plus b squared. Okay. So since the logarithm is well defined for positive real numbers, so we would have x equals 1/2 ln of a squared plus b squared. Okay. So that means we take the logarithm of both sides. So if a is not 0, we can have this here. Tangent of y equals b over a, and that is equal to y equals tangent inverse of b over a. So that means this is the way on how to get the value of the certain angle. Therefore, we would have a final formula. Z equals 1/2 ln of a squared plus b squared plus I tangent inverse of b over a. And this one thing here, this z here, this is a solution to equation of the form e to the z equals a plus b I or ib. So this is now our formula to remember. So now that we have derived the formula for getting the solution of the form e to the z equals a plus bi, we will have to apply for an example for this. But before that, we will have to continue first some discussion that this holds for a case when a is not 0. How about if a is 0? Okay, so what happens if a is 0? Then e to the z is 0 plus ib, or that's equal to ib. Okay, now so e to the x, remember that that's equal to the modulo of b, and your y is equal to the arg of e to the z, and that's equal to arg of ib. So in this case, we have additional formula. Your z here is equal to ln of b plus I pi over 2 plus 2k pi if b is greater than 0. Now, if b is less than 0, then we would have this case here. Okay, so that means to say that if it's greater than 0, your pi here is positive. If b is less than 0, your pi here is negative, pi over 2 I mean, and everything else are the same. Okay, so we will apply an example now. Let's say e to the z is equal to negative 5 plus 5i. Okay, so what happened is we will use the formula. So by using the formula above, I would have z equals 1 half ln of negative 5 squared plus 5 squared plus I tangent inverse of 5, rather 5 over negative 5. Okay, so this is simply this is actually 50. So I have ln of 50 over 2 plus I. And remember tangent inverse of 5 over negative 5. So that's technically tangent inverse of negative 1. So that's a negative pi over 4. So meaning to say we have pi over 4, and it's a multiple of 2k pi. Your k is in the set of integers. So always remember that your z is an integral multiple of 2k pi. That's it. Okay, so the complex case holds the same for real case in terms of trigonometric functions. So if you notice, you have sine y in this form, and you also have cosine y. So instead of using y, you use z, then that will also hold here. That's it. And we also have to take note that e to the z bar, so that means the conjugate of e to the z, it's the same as e to the conjugate of z. Okay, so let's solve this example here. So find all the complex numbers for which cosine of z equals 2. So solve on that. Remember that cosine of z, I can write that as e to the I z plus e to the negative I z over 2. That's equal to 2. So if I'm gonna simplify that, I would end up having e to the 2iz minus 4 e to the iz plus 1 equals 0. So, which means we have quadratic in e to the iz. So, solving for e to the iz, I would have 4 plus or minus square root of, this is 16 minus 4 over 2, and that's equal to 2 plus or minus square root of 3. So if you have any questions or clarification, you can comment down there. Let me double check. Yes, that's it. But remember, e to the iz, I can write that as e to the I x plus iy. And so I have e to the negative y times cosine x plus I sine x. And remember, this is equal to 2 plus or minus square root of 3. So this simply tells us that e to the negative y cosine x is equal to 2 plus or minus square root of 3, and your e to the negative y sine x is 0. Now observe that this one here implies that our x is equal to n pi for some integer n. Okay, so if that is n pi, this simply tells us that n must be even. So e to the negative y equals 2 plus or minus square root of 3y. What happened? Because it says here that n must be even, so the cosine of this n pi, because x is equal to n pi, is equal to 1. So that means we have ended up e to the negative y equals 2 plus or minus square root of 3. This further tells us that your y is equal to negative ln of 2 plus or minus square root of 3. Hence, cosine of z equals 2 if and only if our z here is equal to 2k pi plus I ln of 2 plus or minus square root of 3, which is equal to 2k pi plus or minus I ln of 2 plus square root of 3 for some integer k. Okay, so before we end this video here, we will have to introduce first these hyperbolic trigonometric functions on complex numbers. So I'm not gonna derive them all because they're actually easy and pretty obvious following the same rule we've discussed earlier. So it says here that the hyperbolic sine of z is equal to e to the z minus e to the negative z over 2. And if you change plus in between e to the z and e to the negative z, that's actually a hyperbolic cosine of z. So by this identity here, This further implies that your hyperbolic sine of z is equal to the I sine of iz. So that means there is an additional 4z here. And for cosine hyperbolic of z, that's equal to cosine of iz. Lastly, the sinh of negative z is equal to the negative sinh z, and the cosh of negative z is equal to cosh z. So this only tells us that this is an even function. Okay, so that's all for now. Thank you so much for watching. If you have any questions or clarification, don't forget to comment down so that I would know, and in that way we can discuss on that. So guys, thank you so much and have a great day to you. Bye for now.